Hello everyone, welcome back to our openEuler mini course. I'm Irene, and in today's course, I'd like to introduce shared virtual memory, SVM, which is the same thing as shared virtual addressing. Before we jump into SVM, we must first understand direct memory access, DMA. DMA is a feature of computer systems which allows devices to access system memory directly without going through the CPU. This type of memory access is commonly used in embedded systems, where it plays an important role in reducing latency and improving system performance. In traditional DMA, the CPU is responsible for setting up the DMA transfer, then handing off control to the DMA controller, which then controls the entire transfer process. This feature is useful when the CPU cannot keep up with the data transfer rate, or when it needs to perform work while waiting for a relatively slow I/O data transfer. The traditional DMA approach offers better system performance, reduced latency, and increased system scalability. Traditional DMA, however, allows memory to be accessed through physical addresses, which is likely to introduce problems. For example, an illegal address may cause information leakage or data damage. Memory fragmentation may cause physical addresses unavailable because of high continuity requirements. And limited device address bit widths may cause limited address range. With the emergence of complex scenarios that demand high computing power, such as assisted driving, GPU workloads, encryption and decryption, image encoding and decoding, and complex operations. In addition, even greater number of tasks are loaded onto acceleration devices, requiring increased data interaction between acceleration devices and CPUs. This process is made simpler with IOMMU. In computing, IOMMU stands for Input-Output Memory Management Unit. An IOMMU, a type of hardware used to provide memory protection for I/O devices, connects a DMA-capable I/O bus to the main memory. Like a traditional memory management unit, IOMMU maps I/O virtual address IOVA to physical addresses. Different platforms have different IOMMUs. Examples of IOMMUs include the Intel IOMMU, Graphics Addressing Remapping Table, GART used by PCI Express graphics cards, and System Memory Management Unit, SMMU, used by the ARM platform. An IOMMU prevents data corruption and security breaches by restricting access to memory, only allowing the processor to access memory that is allocated to the I/O device, but address translation and page fault, handling increased performance overhead. In addition, an IOMMU allocates space for the I/O page table. To avoid memory overhead, the IOMMU and CPU may share the page table. For example, a device and CPU may share the virtual address. We've mentioned the DMA and IOMMU, but what SVM is exactly? What's the relationship between SVM and these two techniques? SVM is a memory management technique used by multiple applications or processes to share physical memory resources. Let's take the ARM-based SMMU as an example to give a detailed description of SVM. SVM works by creating a unified address space that allows multiple devices or applications to access the same physical memory. This is done by assigning a virtual address to each device or application, and then mapping that virtual address to the physical memory address. This unified address space is managed by the SMMU, which is responsible for ensuring that the shared memory is used efficiently and that there are no collisions or conflicts between the virtual addresses. SVM allows for better performance and memory utilization, as well as more flexibility in how memory resources are used. Here is another question. How does SMMU ensure that SVM is working properly? One platform may have multiple SMMU devices, and each SMMU device may be connected to multiple endpoints. In this case, multiple devices may not reuse the same page table and need to be distinguished. The SMMU searches for the corresponding stream table entry, or STE, in a stream table based on the stream ID to distinguish different devices. In addition, multiple processes with the several page tables may use a device. Therefore, the device must be able to distinguish page tables. The SMMU use substream IDs to distinguish the page tables. The figure presented here shows an example of two-level stream table. Typically, an STE contains a pointer pointing to a stage 2 address translation table and a pointer pointing to the context descriptor. Simply put, a stream table is stored in memory and is created by the driver when the SMMU device is initialized. As shown in the figure, a two-level stream table is split into two levels for indexing, which saves memory. When two-stage address translation of the SMMU is enabled, the virtual address sent by the device DMA request is translated into the intermediate physical address IPA in stage 1, and the IPA is used as the input of stage 2. In stage 2, the IPA output in stage 1 is translated again to obtain the physical address. In this way, the DMA request correctly accesses the address space to be operated by the guest. The aim of a two-stage address translation of the SMMU is to support SVM in virtualization scenarios. SVM allows each process on a VM to independently access a pass-through device that is directly associated to the VM and initiate DMA requests to the device in the process's own address space, which can reduce application programming complexity and improve security. In virtualization, a guest OS can use hardware that is not specifically made for virtualization. Higher performance hardware, such as graphics cards, uses DMA to access memory directly. In a virtual environment, all memory addresses are remapped by virtualization software, such as openEuler, which causes the guest OS fail to access memory using DMA. However, IOMMU can handle this remapping, allowing drivers to use DMA to access memory from the guest OS. To implement SVM in virtualization scenarios, openEuler needs to simulate a vSMMU or VIOMMU. When an internal process of a VM needs to access a pass-through device, the VM invokes the guest driver to create a process address space ID table, or PASID table. The PASID is used as an identifier of the process address space in a VM. When the device initiates a DMA request, a PASID prefix is carried with the request. In this way, the SMMU can distinguish devices. When a PASID table is created, the vSMMU is accessed. In this way, the guest driver transfers the PASID table address to openEuler. Then openEuler sends the table information to the SMMU through the IOCTL call of VFIO. In this way, the SMMU obtains the shadow information of the PASID table of the guest internal process and can create a stage 1 address translation table. If you are interested in the detailed description of this process, you can read our blogs in the openEuler community. Using SVM may increase costs for setting up and managing a shared virtual memory environment or limited scalability by the underlying physical memory resources, but it is still an ideal choice for allocating physical memory resources between multiple applications or processes. It offers several advantages over other memory management techniques, such as, first, improved performance and memory utilization. By sharing physical memory with multiple applications or processes, the overall system performance can be improved and memory utilization can be maximized. Second, increased flexibility. By having a unified address space, applications and processes can access the same physical memory without worrying about conflicts or collisions between addresses. Third, reduced fragmentation. By using virtual addresses, the physical memory can be allocated more efficiently, resulting in less fragmentation and improved performance. Fourth, easier memory management. With the SMMU managing the unified address space, memory management can be simplified and automated. Well, that's all for today's course. I hope you found this insightful and that you are now better informed on the topic. If you are interested in Linux kernel or openEuler, please visit our SIG page and stay tuned for more mini courses. Thank you for watching.